Our center is dedicated to fostering joint R&D collaboration between United States and Korean industries and researchers with a strong focus on translating innovative ideas into impactful technologies. With that, let me briefly introduce today's speaker. It is my great pleasure to introduce Dr. Akanksha Menon. Dr. Menon is a assistant professor in Woodruff School of Mechanical Engineering at Georgia Tech. Her research focuses on sustainable water and energy system combining thermal engineering and material approaches. She leads the Water Energy Research Lab and actively collaborate with leading national laboratories across the United States. Again, it is our pleasure to have her with us today. So I will hand it over to you, Dr. Menon. Dr. Menon, please go ahead.
Perfect. Thank you so much, Karam, for this introduction. Hopefully you can hear me well. Okay, great. All right, so yeah, as Karam said, I'm Akanksha Menon. I'm an assistant professor in the Woodruff School of Mechanical Engineering at Georgia Tech. My expertise is primarily in thermal science and engineering and utilizing functional materials, phase transitions, and different materials for clean energy and clean water. So today I've put together some slides to discuss the different projects that we work on. All right. Yeah, so today I'll talk about the work we're doing on developing some materials and systems for clean energy and clean water. So it's just an overview of different projects to give you an idea of the things we're interested in. So my group looks at water and energy. So on the water side, mainly we develop systems for desalination and brine concentration. So here we're leveraging phase change or phase transitions in specific materials. So liquid vapor phase change associated with, just evaporation, condensation. And then we also have some work on liquid-liquid phase change, where we use thermally responsive liquids, like ionic liquids and deep eutectic solvents. And then we also have some work on membrane separations for desalination. We're also interested in resource recovery. So when you extract most of the water from a desalination process, you can get a brine that is rich in minerals of interest. So that can be for lithium recovery, as well as some critical materials and rare earth elements. So that's something else we're very interested in. On the energy side, we do a lot of work on thermal energy storage. So these are essentially thermal batteries because we're storing electricity or heat in them, but then releasing it as heat at different temperatures. So for lower temperatures, we release heat for like buildings, heating in buildings, or for hot water. And then higher temperatures, we release heat for industrial process heat as well as for power generation. So we use different types of phase transitions here. So some latent heat materials as well as thermochemical materials. And then in this case, we're very interested in studying as we cycle them. So you charge, discharge over thousands of cycles. How does the performance get impacted? And then we're also doing a lot of work on thermal management. So this is mainly in the context of data centers and looking at how do you move the heat that is generated at the chip level to the rack, the server rack, and then finally out of the building. So thermal management across those different length scales. As well as some work on waste heat recovery and reuse. So depending on the temperature of the heat, can you then use it, convert it either to electricity or use the heat to produce cooling in an absorption refrigeration type of system. So across all these projects, mainly we do thermodynamics and then heat and mass transport as well as charge transport modeling, build like lab scale test beds, and then finally do a little bit of just cost analysis to see does it make sense. But ultimately, we're combining thermal science concepts with these functional materials that have interesting phase transitions to be able to do clean water or clean energy. So in this presentation, I'm going to focus on like three of these areas. So first, we'll start with thermal energy storage or these thermal batteries. So the reason why we're interested in this topic is mainly to decarbonize heat. So if we look globally at energy consumption, 30% of energy is used for the transportation sector, 20% for electricity generation, and then 50% of the energy is used in the form of heat. And that's for buildings as well as for industrial processes, almost 50-50. And over 90% of that heat comes from burning fossil fuels. And in this case, we're interested in looking at using that heat again for buildings or for industrial process heat. And you have to be able to deliver heat at a range of different temperatures. So how do we provide heat instead of with fossil fuels, provide heat at many different temperatures? So for that, we use low-cost, large-scale energy storage. So specifically, you can take any form of energy, whether it's solar, wind, electricity from the grid when it's available, use that to charge the material. So this is our thermal energy storage. Just think of this as a black box for now, but charge it with electricity, and then that is stored as heat within the material. And then when we want to release it, we would introduce a gas to release the heat from the stored material to get either high temperature heat for manufacturing or lower temperature heat for buildings. And depending on the material we choose and the type of storage, that controls the temperatures that we can get for process heating or for buildings. If you have very high temperature heat, we can also take that, convert it into electricity with a heat engine, any kind of power cycle. So there's three different types of thermal energy storage. The simplest version is sensible energy, so just storing it in a temperature difference, like heating up water. And then there's phase change or latent heat energy storage, where the material undergoes some phase change. So for example, melting ice to liquid water. And then the final kind is a chemical reaction. So endothermic, exothermic chemical reaction for energy storage and release. And if we compare how much energy you can store, so if I want to store 10 gigajoules of energy in any of these three types, you can see the volume of material needed is very different. And these thermochemical materials are the most energy dense. So you can get very compact energy storage solutions by using chemical reactions for heat storage and release. For all of these cases, we need the energy density to be high. We also need high thermal conductivity, high electrical conductivity, so we can charge it with electricity. And then most importantly, we need cycling stability. So as we charge and discharge over hundreds and thousands of cycles, how does the performance change? So that's what we study specifically with these thermochemical materials or TCMs. So you start off with one solid structure. So let's say low temperature, we mainly work with salts, salt hydrates. So essentially it's a salt that has a certain number of water molecules attached to the crystal structure itself. And if we heat up the salt, it gets dehydrated. So that's a desorption reaction. So desorption and the water vapor, which is the gas in this case, will leave. So this is how we charge because we've put energy in. And then we get a second crystal structure, the new phase. And then when we want to discharge, we would reintroduce the gas. The sorption reaction occurs. This is exothermic, and so heat is released in this reaction, and that is the heat that you would use for your process. So instead of like a salt with water vapor, we can also have something like calcium oxide or calcium carbonate which will desorb CO2, so carbon dioxide, and become calcium oxide, and then reintroduce the carbon dioxide to form calcium carbonate or limestone. That is a very high temperature reaction, like around 800 degrees Celsius. So we study that for industrial process heat. Again, the main benefit of these materials is very high volumetric energy density. And also the storage is lossless because it's a chemical reaction and all the energy is stored in the chemical bond. So there's no self-discharge over long durations of storage. And we work with materials at a very low cost. So like I said, limestone and salts. So these are very abundant and non-toxic as well. What we study are putting these into reactive beds. So this is an example of a packed bed reactor where you have some inner pipe for fluid to flow to either charge or discharge. And then you have your particles, which are the salts or the limestone. And these are packed in some packing density. And so you have between the particles, you have transport occurring. So that's interparticle transport. And then within each particle, they're also porous. And so you have intra-particle transport as well. So you essentially have heat and mass transport within this type of reactor at these different length scales. There's diffusion, and then there's chemical reaction as well. And so all of these coupled effects is what we model using heat and mass transport models, as well as chemical kinetics or rate models. And then we develop lab scale prototypes of those systems to test the performance. So I'll show you some examples of what we have. So in terms of the materials, we make some composite materials to stabilize the salt. So for example, we take salts and impregnate the salt within a porous matrix like silica. And the silica has pores that are very small, so nanometer size pores or mesopores. If you put salt into mesopores, if the salt forms a solution, it cannot leak out of the pores because of capillary attraction that keeps it within the pores. And so the salt remains within the mesopores of the silica. And then between the silica particles, we have like larger macropores where water vapor can transport in and out. So essentially, we nano-confine the salts in a mesoporous matrix and allow the water vapor to transport. So this gives you a very stable composite that you can cycle hundreds of times. You can also form these types of encapsulated structures. So if you have a polymer matrix or a hydrogel, you essentially put the salt within the hydrogel matrix, and the hydrogel has mechanical flexibility or elasticity. So as the salt hydrates, it undergoes volumetric expansion, and the hydrogel expands to allow the hydration. And then when you dehydrate, you can contract, and the salt has that space to move as it expands and contracts. And there are also pores within the matrix to allow for the water vapor to transport and allow the chemical reaction to occur. This is what it really looks like. So here, this is with an alginate matrix. And you can see these large pores for water vapor transport. And then you can see the small white particles that are embedded inside the matrix. And that is essentially the salt. And so this is another way of just like stabilizing the salt into a composite. And this allows us to cycle it over several charge-discharge cycles. So this is some of the work we're doing on the materials level. And then we also have different lab scale systems that we've built in order to run the actual chemical reaction. And so we have, different mass flow controllers for the gases, as well as some humidity control, and then heat exchangers to get to the right temperatures. And then we have all of this to precondition your gas and then introduce it into the reactor. And here are some of the prototypes of the lab scale reactors that we have. This is about 100 grams of material that we test with thermocouples in order to measure how much temperature increase we get or temperature lift, as well as how much power we can generate, thermal power output from these different types of reactors. So packed bed, as well as some fiber-based like shell and tube geometries, and then also some cycling of the material under very controlled environments. For the high temperature systems, we've also developed a capability to do rapid cycling. So we want to cycle from room temperature up to 800 degrees Celsius and do thousands of cycles within a week. So if you do this in a TGA-DSC or in a tube furnace, it will typically take months to get the data for a single sample. So what we're focused on is to develop a way to do 1,000 cycles within 1 week. So heat up the material, cool it down, cycle it thousands of times to study its performance. And so here you can see the reactor that we've built to do rapid cycling. And we use direct joule heating. So give current directly to a porous carbon heating element, and the porous carbon heating element heats up, goes up in temperature. So you can see it's glowing here because it can go up to about 1,200 degrees Celsius and very rapidly come back down and repeat this thousands of times. So it's all within like a quartz tube to hold everything and seal it from the external environment. And we have this PID control that we've developed to give us very rapid heating and cooling rates. So here you can see the real experimental data. So going up from about 650 to 850 degrees Celsius in less than or in 1 second, and then maintaining that temperature very, very carefully, and then cooling back down within about 15 seconds. So you can do 1,000 cycles within a week to study these thermal batteries at very extreme temperatures. So now let's shift gears and talk a little bit about the work we're doing on the desalination or brine concentration side. So why we work in this space is really because, of course, there is a lot of water on the earth, but only a very small fraction of that is actually available as like fresh water that we can readily use. So most of the water is actually in the form of ocean water, 97%. And so if we can desalinate ocean water or any kind of industrial wastewater and reuse it, that would be very beneficial. And this is also mainly to like combat water stress, right? So projections for water stress by 2040, and you can see across the globe, these high darker colors mean higher water stress, which means more water than what is available naturally is being consumed for different processes. So desalination is one way of augmenting or increasing the freshwater resources. But we have to look at technologies that can make sense at a large scale and a low cost. So traditionally, how it's done is you can use reverse osmosis. So these are, membranes that you have your saline water come into. So typically seawater, 3.5 weight % salinity. Reverse osmosis can extract about 40 to 50% of that water. And then you're left with the brine, which now has like twice the salinity, so 7 weight %. What do you do with this brine? If you cannot discharge it to the ocean, you have to do a brine concentrator. So this is a thermal process that uses mechanical vapor compression. So you essentially evaporate, take the vapor, compress it, and reintroduce it. And that way you can get 80 to 90% of the water recovered. and you get to this state called minimum liquid discharge, or MLD. So very high salt concentration here, 28%. And then finally, you can put that, let's say, in an evaporation pond and just allow the remaining water to evaporate under the natural sunlight till you get to the saturation limit and the salt precipitates out. This is how it's conventionally done. This is called zero liquid discharge because you've taken out almost all the water, like over 98% of the water, and you're left with a very concentrated stream of minerals like salts of interest, as well as critical materials like lithium and some rare earths. The disadvantage is this process is very energy intensive, and mostly it uses heat exchangers here, as well as for the evaporation ponds. And the heat exchangers corrode under these very high salt concentrations. So you have to use very specialty alloys in order to make it function. So we are really focusing on how can you do this brine concentration as well as crystallization in a much more efficient way and in a more low cost manner. So we've developed a process called air gap diffusion distillation, or AGDD. It's actually a very simple concept where we have an evaporator surface and we have a condenser channel that face each other. It's a vertical orientation. Through the condenser channel, we flow the salt water up, so pump that up. And then if we need, we can add some external heat. And then the heated brine, the salt solution, flows down the evaporator surface. As it flows down, this is at a higher temperature than the condenser. And so there is a driving force that causes vapor to diffuse like falling film. And this is your permeate or your fresh water distillate. And then you have this brine stream. So we can recirculate this multiple times. And as it condenses on this surface, it releases the latent heat, which is used to preheat the feed flowing up. So everything operates at atmospheric pressure, and you have latent heat recovery by using like a counterflow heat exchanger configuration. So 90% of the energy is recycled and only 10% needs to be added externally. It's entirely made out of plastic surfaces, and so you have very low surface energy, polymeric surfaces with very low surface energy, and so corrosion is not an issue, and you also have very low like scaling because of the low surface energy. So no membranes, no metallic heat exchangers, just using plastic surfaces with heat recovery integrated. We also work like beyond evaporative desalination. We look at some thermally responsive liquids. So these are liquids that have a special type of phase behavior called a lower critical solution temperature, or LCST, phase behavior with water. So what I mean by that is this is the phase diagram. So this curve is the LCST curve. So at a low temperature, let's say we're here at state 2, here you have a mixture of water and either an ionic liquid or a deep eutectic solvent, and they're fully mixed, so a homogeneous mixture. Once we heat it up to a certain temperature, we go above the phase boundary and it splits into the two phases. One phase is water rich, so WR is water rich. The other phase is ionic liquid rich, so that's or organic phase rich, so that's over here. There is a density difference between the two phases, and so you will get a liquid-liquid phase separation where one phase floats on top of the other. So just by using heat, you can go from the fully mixed state to these two separated states, and no evaporation. It's just a liquid-liquid phase separation. So we've done some work to study microscopically what's happening. So it behaves almost like a colloidal mixture, where first these small particles form of one phase, or droplets of one phase form within the second phase. And then as you keep increasing the temperature by providing heat, that small droplets will start to coalesce. And once they coalesce, they form larger droplets, and then you start to form two macroscopic phases. With the ionic liquids, they're more dense, so they settle at the bottom, and the water-rich phase is on top. So we can use this liquid-liquid phase separation also for these desalination applications. So we've built like lab scale prototypes with this. So for like the air gap diffusion distillation, you can see some of these like plastic heat exchangers, heat and mass exchangers, because vapor also has to move through. And then these fans are really just to blow the air through these devices. So these are some of the prototypes that we've built to demonstrate desalination and brine concentration all the way up to saturation conditions, so zero liquid discharge. And then we also have a reverse osmosis setup. So this is the membrane module itself is over here. So these are spiral wound RO membranes, and we've assembled the high pressure pump. So this is a 1 kilowatt system, as well as some like pre-filtration or pre-treatment, and a lot of the instrumentation like flow controllers, pressure gauges, and a back pressure regulating valve. And this particular system, what we've done with it is we're operating it as a batch system where we have power electronics to really control the power through the pump, so that you're increasing the pressure gradually and having variable pressure operation to see what does that do to the performance of the membrane-based system. So if you can do variable pressure reverse osmosis, you can integrate it with renewable energy sources, and you can also you can also get much better performance than a constant pressure reverse osmosis system. We're also looking at pulsed flows. So if you can pulse the flow, you can actually control the scaling and fouling that happens on the membrane surfaces. So that's something else that we study. And for the final topic, I want to focus on the work we're doing on thermal management. So this is in the context of data centers. So why do we care about this area? So data centers really are the intersection of water and energy. So a lot of the work we do. And the reason why this has become more and more of a thermal issue is because if we look at the power densities for the planned racks, right, like from companies like NVIDIA, for example, you start to see that the kilowatts per rack is going up significantly. This is on a log scale. So it's gone from about 10 kilowatts from a rack to 100 kilowatts per rack currently, and now projecting to 1 megawatt of power within a rack. And so the future data centers will have, they'll be as large as about 10 gigawatts within the entire data center, with multiple 1 megawatt racks within it. All of this power is converted into heat at the data center. And so this thermal energy has to be rejected to the ultimate heat sink, which is the ambient. And so thinking about how we move the heat from where it's generated all the way to the outside is really critical. We also have to keep track of the heat fluxes at the chip level, at the rack level as well. And not just the average heat flux, but if you have a peak, or a hotspot, how do you manage some of those transient heat dissipation? So for that, we really think about this as doing thermal management or cooling across length scales. So at the chip, you may have the highest temperature And then at the rack, you're coming out at a lower temperature, and then ultimately you go to the facility level where you're rejecting to the ambient. But you're also increasing in the amount of energy at each of these length scales. So typically, these are just what's conventionally used. Your servers at the chip level, you can have just air cooling, but now it's become direct-to-chip liquid cooling using cold plates. And at the rack level, you can have these rear door heat exchangers, which again, mostly for the air-cooled systems, but now we're looking at these coolant distribution units where you have these liquid loops going to each server tray. And then at the facility level, traditionally, it's been a lot of cooling towers where you have to evaporate large amounts of water. But now we're looking at dry coolers with a little bit of evaporation or adiabatic assist, and chiller only when you need it, depending on the climate and the location. So we've just mapped out all the different thermal management technologies or cooling technologies at the chip level, depending on the power density. So again, we've gone from air cooling to single phase cold plate cooling. So with water, for example, or water and glycol mixtures. This is where we are currently. With a microchannel, you can get much higher heat fluxes. With water, again, just because you're increasing your heat transfer coefficients. Same for like jet impingement. And then immersion cooling is still somewhat, early stage, not commercially used, but you can do single phase or two-phase immersion using some refrigerants. But these typically do not perform as well as water, because the thermophysical properties and the latent heat of these refrigerants and dielectrics are much less than just water. So we have this roadmap that we've developed for the chip level thermal management. And then to work with the transient peaks that occur. So if you have a large spike in power, a thermal system cannot respond quickly. A thermal system takes a longer to respond. And so you need some kind of a buffer to take the thermal load and then dissipate it over a longer time scale. So phase change materials are really suitable for this, because phase change materials, by definition, when you have phase change happening, you maintain the temperature. So it'll keep the temperature at the safe operating limit and acts just as a thermal buffer to undergo like melting. And then that melted phase change material has to re-solidify by rejecting the heat, but you're essentially just increasing the time scale. So we've looked at so essentially just a heat sink, a traditional like aluminum heat sink with localized heat spots to simulate like a hotspot on a chip. And we have some phase change material in there, and we can study how much of the phase change material is active. So how much is melting and re-solidifying under a transient spike. So within a few seconds to a minute, how is it able to absorb the heat? So we study the cycling behavior, because again, you want something that can be cycled thousands of times. So in this case, a much smaller cycling range of temperatures, because we're operating within the electronics temperatures. And you can see the sensible cooling and heating versus the latent cooling and heating. So where we have the constant temperature is indicative of the phase change happening. We can control not just the temperatures and the ramp rates, but also how quickly these cycles happen to really study how the material is responding. And then we encapsulate the phase change materials. So the PCM is like within this shell, and that shell is just preventing the material from leaking out as it melts. So that way you're working with like these smaller spheres of phase change material that can melt and solidify quickly rather than like a large amount of the PCM. So that's just a macro encapsulation technique that we use. We also do something with thermoelectrics. but we're using thermoelectrics very differently. So typically, you have your heat source here and a cold plate on the bottom, and you have your thermoelectric material, so a P-type and an N-type semiconductor connected like this. So this is the thermoelectric in the off state. And so it's off, meaning that there's no current being supplied to the thermoelectric. So we have the heat source at almost 39 degrees Celsius and the cold plate at almost 20 degrees Celsius. When we turn on the thermoelectric by feeding a current, so providing a current to it, you immediately see that most of the temperature is actually dissipated. So the highest temperature now is like closer to 24 degrees Celsius, except where we have the heater itself, right? So this is the same heater at 39C, but you can see where the thermoelectric is actually a lot colder. So this is active cooling, and it's not using typical bismuth-telluride semiconducting thermoelectrics. We're using metallic thermoelectric materials. So you're using a current to move more heat, but in the natural direction from hot to cold. So not refrigeration, but active cooling. So this again is a way in which you can just source a current, very quickly dissipate a hot spot using a thermoelectric metal. So this is based on iron and nickel alloys rather than traditional bismuth telluride. And essentially what it's doing is it's increasing the effective thermal conductivity of the thermoelectric material. So this is something else that we've been working on. At the rack level also, we look at the different cooling technologies. So again, moving from traditional air-cooled heat exchangers and components to a lot of direct-to-chip, so liquid cooling. And we're actually in the process of extending this to a 1 megawatt rack and seeing which technologies with what kind of flow rates and fluids allow us to do cooling of a 1 megawatt rack without reaching erosion limits, so maximum flow rates. And finally, at the system level, we look at how do you reject the heat to the outside. So cooling tower consumes a lot of water, but less power. And so in water stress locations, you cannot use a cooling tower. And a lot of the new data centers are being located in regions that have water stress. So we're looking at dry cooling, where essentially this is just like a large, radiator, car radiator, where you have a fin tube heat exchanger and you're consuming power for the fans to blow the air through it, but very little water, only in the form of what we call adiabatic assist. So like a little bit of a spray, water spray, or a soaked pad to pre-cool the air in certain locations. And the chiller, again, using that only when you absolutely need it, because the power consumption is very significant to do mechanical refrigeration. So we have models for these dry cooler systems with and without adiabatic assist, just modeling the performance in different climates. This is in the US. So in a dry climate, like in Arizona versus here in Atlanta, which is more of a humid climate, and seeing when can you do just full dry cooling versus when do you have to consume water to reject the same amount of heat. And in the summer months is typically when you have to consume more water because your ambient temperature is too high to just reject heat by dry cooling. And so we can analyze this for different locations and different times of the year. So with that, I just want to acknowledge like all the work that's done. All this work I presented is done by the students in my group, as well as like some of the funding sources that we have that have supported these projects. And I have my email address as well as the lab link if you're interested. This QR code also will take you to the same lab website or lab webpage to see these projects. So thank you so much.
Thank you, Dr. Menon, about your great talk. Uh, I will, now we are moving on to the Q&A session.
Sure.
Uh, if you have any questions, please uh, click the raise your hand and I will let you talk. All right. During their thinking about their questions, I actually have a question for you. I was really impressed that how clearly you explained about the chip level, rack level, and facility level. So what am I still having trouble grasping is the scale of thermal energy storage materials.
Mhm.
How much quantity are going to be used for each level?
Yeah, so thermal energy storage, if you do it with thermochemical, right, which is like with this version, thermochemical is
Hmm.
very, very energy dense. So these, you like to store 10 gigajoules, you need like less than 5 cubic meters, right? So this can be done fairly large scale to store large amounts of heat in a very small amount of volume. But the challenge with them is the cycling behavior. So the cyclability, as you charge and discharge hundreds and thousands of times, we see that the performance degrades. So most of what we've been focused on is like how do you stabilize the material so that it is very energy dense, but how do you stabilize it to last for thousands of cycles?
All right. I have another question. So it's about the air gap distiller.
Sure.
So, um, I think it's really great. It's and scaling the air gap distiller to the size of existing industrial level, like industrial heat exchange,
Mhm.
sounds promising. And what are the main challenges are going to be anticipated during the scaling up?
Yeah, so this version, this is like the unit cell, right? So one
Mhm.
module is this. So in a realistic system, you would have many of these in parallel with each other to scale up your capacity, but they're all vertically stacked. So the versions that we've been modeling is like a meter tall, so 1 meter tall, and about 0.2 meters deep, and you would have like tens to hundreds of these stacked to get to the capacity that you want. So the in terms of the challenge, so we've demonstrated experimentally. So the recent paper we had that came out last month showed the full process to do brine concentration and crystallization, even over a long duration. So we ran the experiment nonstop for over a week and showed the performance was very stable. So the next step to scale it up to a real practical process is we have tested it like mainly with just a simple salt solution like sodium chloride, but real industrial wastewaters can have many other components in them. So we want to be able to test with like real wastewater sources and see how it performs in those cases.
Okay, thank you. I actually got a questions from the audience. And do you have current industry partnership in Korea right now?
I do not. For context, my lab is like only 5 years old now, right? So it's still a relatively new group. So I don't have any industrial partnership in Korea, but I'm very interested in working on industry projects. So all the projects or all the funding right now has been from the US, including the industry projects we have with Google and Novellus is based here.
All right. We have one audience want to talk about.
So, can you hear my voice?
little bit echoing, but it is great.
Yes.
Sorry, can you hear my voice?
Yes.
Uh, so, uh, I'm the Korea finishing and I'm in the institute in Korea, so KIAT. So my major is water treatment in the in the air gap, the membrane system. So it is the reach it to the general the concentration system and how efficiency of this system in the lab scale or some pilot scale. So can you explain that?
Yes, sure. Yeah, so this version, ours air gap diffusion dissolution, there is no membrane, it's only an air gap. The commercial version is air gap membrane distillation, where there is a membrane in this space. But unlike like reverse osmosis or those processes, in an air gap system, the membrane does no real separation. It's only a physical barrier, but it also ends up getting scaled, like scaling and fouling. So that's why we got rid of the membrane, and instead you just get much better mass transport as well as minimize the heat transport because you just have air as your insulator. So the efficiency of this system is like the thermal efficiency, which is essentially a measure of like how much of the latent heat is being recycled in the system versus what are you adding externally. So it's called the gain output ratio or GOR. And commercial thermal desalination systems have like a GOR of like approaching 15. These are like multi-stage systems. We have shown in these papers that you can get with air gap diffusion distillation, you can get a GOR of up to 12 with this kind of like plastic heat exchanger stacked geometry. So comparable thermal efficiency as like commercial multi-stage systems you can get because you're doing latent heat recovery through the counterflow heat exchanger design.
Thank you very much. I will check the
Okay.
paper.
Yeah.
Thank you. If you have another question, please click on the raise your hand. And like you said before, oh, there's another audience wants to talk.
Okay.
Can I talk?
Yes.
Yeah, hello, Dr. Menon. Thank you for participating today's presentation. I'm the Chief Representative of KIAT US office. So we
Okay.
are co-hosting this webinar to promote the partnership with the Korean companies, with US researchers as you. So I hope you are enjoyed today's presentation. We are expecting more partnership with the Korean companies through this presentation. So if you have any further questions and things to request, always welcome to contact me. And any questions about our program, anytime you can contact Dr. Ya or me. So I just let you know that as information. Thank you.
Thank you. Thank you for sharing that.
Thank you so much.
Yeah, as I said, we're very interested in setting up new collaborations, especially like industry collaborations, because that's very valuable for students to work on real world problems. And our basic expertise is like in thermal science and functional materials, right? So I showed you examples of the ongoing projects, but we can also like do other types of analysis or build prototypes for other specific use cases.
All right. Is there any questions from the audience? All right. Dr. Menon, thank you for your talk. today. We're really it is our pleasure to have you today. And if you have I hope you have a wonderful collaboration with our Korean industries and companies. Yeah. And thank you all for the audience to participating this tech seminar session. And we're gonna have another session in the middle of July. So please participate for the next one, and we'll bring another talk session with the new subject. So thank you all, and I hope you have a great day.
Thank you so much, Karam, for the opportunity, and thank you all for attending.
Thank you.